All right, hello everybody. My name is Derek Demeter. I'm with the M.O. Buehler Planetarium. Joining me tonight, we have, of course, Frank Kane, our telescope operator. You look really snazzy tonight, Frank.
Thank you. Yes, I got a new Command Division jacket tonight, huh?
Yeah. It almost looks like, Pike's, jacket, right?
That's right. Yeah, we're going to new school now.
Yeah, exactly. Excellent. And of course, just joining us tonight again is our commanding officer, Justin Cirillo. He's our communications officer as well. He's going to be the one that's going to be communicating with you all in our Facebook comments for those that are watching on Facebook. And we also have a special guest with us tonight. We have a person from the Central Florida Astronomical Society, and she is doing some really incredible science with variable stars. Barbara Harris. Thank you, Barbara, for joining us tonight.
Thank you for inviting me.
Of course, we're excited to work with you, and let's explore. Tonight's topic is all about variable stars. But of course, we also have a clear night tonight. Yes, clear night. The sky awakens. We have a sequel to Clear Skies tonight. And this is really exciting for us because, well, we're going to be looking not only at variable stars, but we're going to be looking at some other stuff too. Frank, I know you have a whole list of objects that you have kind of in queue for us to look at. So hopefully this will be another exciting night of observation and exploration. Now, real quick, though, I want to kind of give Barbara a chance to introduce herself a little bit and a little bit about this thing called variable stars and what's special about observing variable stars. So, Barbara, can you explain a little bit what you do and what's the significance of variable stars?
Okay, well, I'll just give a little biography of how I got started in astronomy and how I got into variable star observing. I've been interested in astronomy since high school, and I actually thought of becoming a professional astronomer, but when I started college, I decided I wanted to be a medical doctor. And going through medical school, I didn't really have a lot of time to dedicate to astronomy. But once I finished medical school and my residency, I really got into astronomy full time. Also, once I got into astronomy, I wanted to do astrophotography. And even though I loved looking at pretty pictures, I wanted to do more besides just capturing the pictures. I wanted to do some science with my astrophotography. So that's how I discovered the AAVSO, which is the American Association of Variable Star Observers. And even though America is in the name, it's actually an international organization. And it's dedicated to collecting variable star data, mainly from amateurs, but the big recipients of that data are professional astronomers. And usually there's a lot of collaboration going on between the amateurs in AAVSO and the professional astronomers. Because professional astronomers, when they are interested in a particular star, they may get telescope time once a month. And if they're clouded out, that's too bad. They can't collect data that night. But they have a whole slew of amateurs out there that are able to use their telescopes and collect data every night that they can. So a lot of the professionals rely on the data from the AAVSO, these amateur observers. And a lot of times, if the professional astronomer uses data from the amateur observing a particular star, and they publish a paper on it, they will include your name on the paper. So there are several variable star publications that I'm included on just because I've collected data and allowed the professional astronomer to analyze that data. So it's a very interesting organization. And you don't have to be so high tech to observe. The majority of the observers of the AAVSO are actually visual observers. And many of them with just a pair of binoculars or a small telescope. So it goes from anything from just a pair of binoculars or even the naked eye. And one example we'll talk about is observing Betelgeuse. So it goes all the way from there to, uh, I have a home observatory with a 16-inch telescope and a CCD camera. And so it runs the gamut of how technical you want to be. Um, but anybody can contribute. And uh, sometimes people get nervous about, well, I'm not sure I could be trustworthy enough to submit scientific data. But it can be done, and it is done. So it's an interesting organization, and especially if you want to contribute to science.
Yeah, and of course, I think the term that is mentioned is this thing called citizen science. The idea that you, the citizen, can contribute to the scientific understanding of the universe, and variable stars is a good situation. So a variable star is basically a star that does what exactly? So a variable star is something that brightens and dims and brightens and dims, right? And then there's different ways that happens, right?
Right. I mean, I could go right into my lecture, and we can define that if you'd like. So,
Sure, we have I think we're waiting for it just to get a little bit darker, right, Frank?
We're ready to go whenever you are, actually. So, when we get to some of these stars we're going to talk about, we can get some live views. So,
Okay,
I'll let
fantastic.
you know when we can.
yeah, and I think the first few are not up anyway. So,
Okay, great. So
Yeah, the
yeah,
first one on your list is our Corona Borealis that I can actually get. So when you get to that one,
okay.
we'll cut to that.
Okay, so let me get started, and this is my first time doing a presentation, so
yeah, no
hopefully
problem.
I'm
Um,
gonna uh, do this correctly.
yeah, so I believe I made you
So I
host.
have to share my screen first,
Yes,
I
if
take
you
it?
could do
Okay,
that, yeah, just click on the share screen and it should just jump right in.
okay. Uh, is my screen visible?
I'm not seeing it. Justin, are you seeing the screen?
No, not yet. Usually it asks which window you want to share. So it should bring up a dialog box with a couple different windows and then select that one.
Okay, it didn't ask me that.
Yeah, I made you
Oh,
a
okay.
co-host. You should be able to share. Yeah, there you go.
There
Perfect.
it
So now
goes.
we're
All
starting to see it.
right.
All right, there we go.
Okay,
Ooh, look at
so
that.
like I said, I'm really into variable stars. Um, One of the things that ancient writers and poets thought was that the stars were unchangeable. This quote from H.A. Ray says it all. Um, After the day is gone, we shall go out, breathe deeply, and look up, and there the stars will be unchanged, unchangeable. And then until about 400 or 500 years ago, uh, this is what everyone thought, that the stars were they were constant. They did not change because they looked at the constellations didn't change. They would look at particular stars. They didn't see any change in those. But we know right now that that is not the case, that stars do change. And those stars are called variable stars. And not all stars are variable, but many stars out there are variable. And a variable star is basically a star that changes its brightness. It fluctuates in a matter of minutes, hours, days, or months or years. And the reason that there is a change in the brightness of the stars could be due to two processes. It could be something inherent in the star itself, something going on in the star itself, or there could be something extrinsic to the star, something in the neighborhood of the star that's causing it to lose its brightness. This is basically a chart breaking down the groups of variable stars. It's a little busy, but basically there are two big groups: intrinsic variable stars, meaning stars that are changing because of something happening in the star itself. And two of the big groups in this, uh, two of the uh, classes in this group are pulsating variable stars. And the brightness of the star is changing because the star is basically breathing. It's getting large and then getting small again. So when it gets larger, it becomes brighter. If it gets small again, it becomes dimmer. So it's basically a star that's kind of breathing. Another group of intrinsic variable stars are called the cataclysmic variables. And these are basically stars that are exploding or just blowing up uh, every now and then. And one of the more common and more popular member of this group are supernovas. They actually are a type of variable stars. They start out as most of the time, very, very, very dim stars that aren't visible to the naked eye. And even with telescopes, um, requires long exposures just to get a glimpse of these stars. And very few supernovas you could identify the star before it actually explodes. But when it does explode, it becomes millions of times brighter than the original star. So it's one of the more common members that the general public knows um, as far as cataclysmic variable stars. But novas, which are stars that become brighter also, but they're not as violent as um, the supernova explosion, supernova stars. Then there are extrinsic variable stars, meaning that there isn't anything going on in the star itself. There's something in the neighborhood of the star that's causing it to become bright and dim. And the most common group in this category are the eclipsing binaries, meaning that there's a binary system and the two stars are orbiting each other. And there's dimming when one star eclipses the other star. And these are a very common and popular group nowadays because many of the eclipsing binaries are discovered to be transiting exoplanets. So instead of two stars orbiting each other, it's one planet orbiting a star that wasn't identified before. So why do we study variable stars? There's a lot of information that we can get from the study of variable stars. And some of the more common ones are stellar properties, like the temperature of the star or the mass of the star. And especially if it's a binary system, it's really easy to get this information from the stars. Stellar evolution is also a good reason to study variable stars because stars are so old. Like our sun is about 5 billion years old, and we have a middle-aged star. So we're not alive long enough to go and observe the whole lifetime of a star, but we can see stars at different points in their evolution and can learn about the evolutionary history of many stars by observing stars that are at different points in their evolution. Uh, Another reason to study variable stars is one group of variable stars that we're going to talk about is called the Delta Cepheus stars. And these stars are actually a type of pulsating variable stars. And it was discovered that if you could find a Delta Cepheus star in a galaxy or globular cluster or some other type of object, that you could actually use that to determine how far away that object is. And like I said, we can discover exoplanets through the study of variable stars. The easiest way to study variable stars is to actually go out and just look at variable stars with the naked eye. And this example is Betelgeuse is actually a variable star. And we're going to talk about Betelgeuse a little bit later. Also, it's been in the news for the last few months. But Betelgeuse is very, very bright, and you don't need a telescope or even binoculars to go out and measure the brightness of Betelgeuse. What you do need is you need to know the magnitude of stars around Betelgeuse. And what you're doing is you're looking at Betelgeuse, and then you're looking at stars around Betelgeuse, and you're determining the magnitude of Betelgeuse based on stars around Betelgeuse. Like in this first example, we compare Betelgeuse to Rigel, which is about 0.6 magnitude, and safe in the lower left foot of Betelgeuse. It's about 2.1 magnitude. So you look at those two stars and you look at Betelgeuse and you try to figure out, well, how does it compare to those two stars? And in the first example, Betelgeuse looks like it's about the same brightness as Rigel. So you're going to record your magnitude as something pretty close to what the magnitude of Rigel is. And then in our next example, which I can't see, this is Betelgeuse, and when you compare it to our two comparison stars, it looks like it's closer in magnitude to the 2.1 magnitude star. And so when you record your magnitude, you're going to say it looks like it's a little bit less, a little bit dimmer than the 2.1 star. So when you record your magnitude of Betelgeuse, you're going to say 2.2 maybe. And then in the third example, it looks like Betelgeuse is between 2.1 and the magnitude of Rigel. And so you try to estimate what the magnitude is based on how much it is, if it's closer to the 2.1 or the 0.6, but somewhere in between those two. And you can download a little manual from the AAVSO called the Manual of Visual Observing of Variable Stars. And you can, this gives you information on how to do this and how to submit your observation if you're interested in this. And we had a lot of new members of the AAVSO that were submitting observations of Betelgeuse recently, because Betelgeuse has been undergoing some strange activity lately. Besides visual observing of variable stars, you could also observe with cameras, CCD cameras or DSLR cameras. And the AAVSO also has manuals on both of those types of cameras and how you could use those cameras to observe variable stars. So what is the AAVSO? The AAVSO, like I said, is the American Association of Variable Star Observers. Even though America is in its title, it's actually an international observation. It was founded in 1911. And it's basically a place to archive variable star observations and to offer this incredible database to professional or even amateur astronomers if they're interested in studying particular variable stars. It's also a big resource for teachers. A lot of science teachers use the study of variable stars to teach different concepts. So it's a big help to teachers also. Okay, one of the more important variable stars, and some people will think this is probably the most important variable star in history, It's called Delta Cephei, and it was discovered by a 19-year-old deaf amateur astronomer in 1784. Well, actually, it was discovered before that, but he discovered that it was variable. And this is the prototype star for a group of variable stars called the Cepheid variables. And unfortunately, it's not up right now. Like this time of year, I'm usually observing it at around 4 or 5 in the morning. But it's a little bit circumpolar. It's in the constellation of CFAS. And there's a triangle of stars near the corner of Cepheus. There's Zeta Cepheus, and Epsilon Cepheus, and Delta Cepheus. It varies in magnitude between 3.49 and 4.36, and it varies over a period of about 5.4 days. And what's important about this particular star is that in the not the 1700s, it was 18, I can't remember the date exactly, but there was a Harvard computer, and computers were women. Some of them had gone to college for astronomy, but weren't allowed to work in the observatories at the time. So what they would do is these women were hired to basically catalog the images and the stars that were captured by the male professional astronomers. And one of these astronomers was Henrietta Swan Leavitt. And she, while analyzing stars from the southern hemisphere, she discovered several Cepheid variable type stars in the small Magellanic Cloud. And by looking at a pattern of these stars, she was able to produce a law. It was called Leavitt's law. And what she observed was that if she plotted the number of days in the period of a Cepheid variable, meaning the period means how often the time it takes to go from bright to dim and then bright again. If she plotted that period to the magnitude of a star, she developed a linear relationship. And since all the stars that she had observed in the small Magellanic Cloud are about the same distance, then that magnitude is actually the absolute magnitude. And the difference is when we look at a star from our sky and we observe it and it's bright or it's dim, we don't know if it's dim because it's far away or if it's dim because it's intrinsically dim. But the absolute magnitude will tell you how bright a star really is. The absolute magnitude of a star basically says, we're going to put this star 10 parsecs away from us. And this is what it would look like if it were 10 parsecs away. So if our sun were put at 10 parsecs, it would be about 6th magnitude, barely visible to the naked eye. So she came up with this relationship between the period of a Delta Cepheid star and the absolute magnitude, which basically tells how luminous the star was. And this relationship was important because later on, Hubble used that relationship to determine that galaxies were not part of our galaxy, that they were basically separate galaxies themselves. Anyway, Delta Cepheid is a very, very bright star. For me, I usually, when I'm getting the magnitude of it, I use just a DSLR camera of about 15 or 20 second exposure. because to evaluate it, you need to have it so that it's bright enough for you to see on your image, but you don't want to overexpose. And on the left is one of my images, and this is actually the star. I guess, is my mouse visible?
Yes.
Yes, I see
Okay.
it.
Yeah, so this is Delta Cepheus, this is Zeta, this is Epsilon. So it's this little triangle that I'm looking for, and this is Delta Cepheus, the star that I'm measuring. This is Mu Cephei, which is called Herschel's Garnet star. It's also a variable star. So usually when I'm taking an image, not only do I measure the magnitude of the star that I'm interested in, I look for other variable stars in the image and measure that also. So you don't have to just concentrate on the star that you're measuring, but especially for a DSLR camera that has a pretty big field of view, like this is 16 by 24 degrees. So it actually has several variable stars. But two of the ones that I follow on a regular basis are Delta Cephei and Mu Cephei, which is Herschel's Garnet star. It's a red carbon star. So this is one of the stars I follow on a regular basis, and I usually use just a Canon DSLR camera. And this is the light curve of Delta Cephei. And a light curve is basically taking a measurement of the star and plotting the time in the x-axis and the apparent magnitude on the y-axis, and you'll see what the graph looks like of how the star is pulsating actually. And like I said, the period is 5.4 days for this particular star. And this was back in 2016. I actually had almost 3 weeks of consecutive clear skies where I did my own little experiment where I went out at 5 o'clock in the morning and I would take an image of Delta Cepheus and I would measure the magnitude. And I did this every morning at 5 a.m. and I plotted my own light curve. And you can tell it's similar to the shape of what the light curve should look like. It has a very, very high, sharp rise to the maximum magnitude, and then a slower decline to its minimum magnitude. So it's one of my favorite variable stars, mainly because of the significance in history. That because of this star, we now know that there are galaxies that are outside of our galaxy, and not just part of our Milky Way galaxy. Anyway, this is the setup that I use just to take Delta Cepheus, just a tripod and a camera. Because the exposures are very, very short, you don't really need a guiding tracking mount for that. So it's easy to just plop this down in the backyard, aim it to Delta Cephei, and take a 15-minute exposure. So it's real simple to do. So you don't need a lot of experience and a lot of fancy equipment to do that. So one of the, besides Delta Cepheus, another very important Cepheid variable is called the V1 variable in M31. And this is what made Cepheid variables so important to astronomy. Edwin Hubble, the namesake of the Hubble Space Telescope, in 1923, was able to observe a Cepheid variable in the Andromeda galaxy. And at that time, the galaxies weren't called galaxies, they were called spiral nebulae. and they were thought to be part of our Milky Way. And the Milky Way at that point was thought to be basically the whole universe. And when they saw these separate galaxies, they called them spiral nebulae. And they really didn't understand the origin of them, but they all thought that they were part of our Milky Way, that they were not separate galaxies. But once Edwin Hubble discovered that there was a Cepheid variable in the Andromeda galaxy, he was able to use that Cepheid variable to calculate the distance to that spiral nebula. And the actual distance is 2.2 million light years. He came up with about 865,000 light years. So it was a little off, and mainly it was off because of the calibration of the Cepheid variable. But even at a distance of 865,000 light years, they realized that something that distant couldn't be part of our neighborhood, that it had to be a separate galaxy that was far, far away, basically. So besides the delta CFAS, this variable in M31 in the Andromeda galaxy is probably the second most common or important variable star that there is. And I have taken images of this this particular variable. This variable is very, very faint. My measurement of it in this image was 19.89 magnitude, and it took me 30 seconds on my CCD camera to get that magnitude. But this particular variable star has a period of about 31 days, and it varies between 18.5 to 19.8 magnitude. And this is something that you're going to need a CCD camera and a pretty big telescope to get. But this is one that I follow, and I'll keep track of also. So with my explanation of these variables, I'm going to show the equipment that I used to obtain that. So like the delta CFAS, I used a camera and tripod. And for the M31 V1 variable, it was my big 16-inch scope with the CCD camera. So that would take some equipment to get.
Real quick, Barbara. So just to compare, if you can go back to that picture again. So Hubble did his studies with, what was the size of his telescope that he was using?
He was using the 100-inch Hooker telescope at Mount Wilson.
So his mirror, or his not mirror, his lens, because it was a refractor, right? He was using a 100-inch refractor telescope. And what's the size of telescope that you're using to take that image of the Andromeda galaxy?
A 16-inch.
So it's just amazing how technology has changed and improved since the time of Hubble. That with a decent telescope, that you don't need to super really multiple expensive on a giant mountaintop to do some of this stuff. It's pretty incredible.
Yeah, it is. And like this was in 1923, and this wasn't that long ago. So it was just less than 100 years ago that we determined that there were separate galaxies out there, and that we weren't all of it. That there were separate these spiral nebulae that were out there were actually separate galaxies that had hundreds and thousands of stars in it. So it's actually incredible what has happened just in less than 100 years. So like I said earlier, Betelgeuse has been important in the last several months. I'm sure a lot of people have been hearing about what's going on with Betelgeuse. Anyway, Betelgeuse is, we knew that it was variable. It was found to be variable by John Herschel in 1836. It has an irregular period of variability, and it's around 423 days. And we're not sure actually what causes most of the variability in Betelgeuse, but it does go from a magnitude of almost 0, which is very bright, to 1.6, which is the dimmer magnitude. And as you know, Betelgeuse is part of the constellation of Orion. It's the left shoulder of Orion. It's actually a very big red giant star, and it's an older star. Like we know that soon in astronomical terms could be in the next million years, but soon Betelgeuse is going to explode and become a supernova. So in October, we noticed that Betelgeuse was starting to dim. And this wasn't too unusual because we know Betelgeuse is a variable star and it does dim. Now, what was unusual about this dimming is that it continued to dim lower than, fainter than what we were used to. Like before, the faintest we'd seen was about 1.6 magnitude or about 1.5 magnitude. But it reached a dim point of about 1.7 magnitude in early February. And this is historically the dimmest that we have ever seen Betelgeuse. And there was a lot of speculation when this started to happen that Betelgeuse was ready to explode and become a supernova, because the theory is that a star, before it explodes to become a supernova, will drop its temperature, and by dropping its temperature, it will appear dimmer. So this dimming was speculated by many people that Betelgeuse was ready to blow. And so people were getting excited that they were going to see a supernova of a star in our galaxy explode, you know. So this was a big deal. But it turns out that they decided it wasn't ready to become a supernova, because when they did spectra of Betelgeuse, they found that the temperature was not cooling. So they didn't think it was ready to blow and become a supernova. But they think that the unusual dimming is basically from a lot of dust that came from the core of Betelgeuse and basically obscured the photosphere of Betelgeuse enough that it became dimmer than normal. So basically, by the first week of April, Betelgeuse was back to about 0.6 magnitude, which is kind of its baseline until it starts to dim again. So there was some excitement there, and it was interesting to figure out what was finally going on with Betelgeuse. So Betelgeuse, like I said, is actually very bright, and you could easily estimate the brightness of Betelgeuse by going out and looking with the naked eye. For me, doing photometry and measuring it digitally, I use a DSLR camera. In this particular image, I used a camera on a tracking mount. But you could also use the camera on a tripod also, because it's so bright that you don't need a long exposure. Like I don't remember the exposure of this, is probably about 10 seconds. Anyway, here's Orion's easy to spot. Here's the belt stars. Here's the sword. The Orion Nebula is in that area. This is Rigel, and this is SAIPH, S-A-I-P-H. It's the 2.1 variable star. that I use as a comparison. I also use this star called Bellatrix as a comparison star. But this is Betelgeuse. So we can see that it's definitely not as bright as Rigel. Uh, uh, and the 2.1 star down here is definitely dimmer than that. This star here is 1.6 magnitude. It's definitely less than that. So on this particular image, I think I took this on the February 3rd, I believe. And I measured it at 1.74 magnitude. So when I actually measured Betelgeuse, this was the time that it was faintest. And you can see when you look at the stars around it, like this is 2.1 and it's fainter. Well, no, that's not this is a 2.1 star. And it's a little bit brighter than that, but it's a little bit fainter than this star, which is 1.6. So this image is basically a 10 or 15 second image. You can take it with just a camera on a tripod, and there's software that you can use to basically tell the software that this star is 1.6 magnitude. So compare Betelgeuse to that star and tell me how faint or bright Betelgeuse is. So it's actually pretty easy to do and submit your observations. And we had a lot of new observers, especially visually, and also new DSLR observers submitting data for Betelgeuse during that 6-month period that it became bright. Now, this is another one of my favorite variable stars. It's called R Corona Borealis, and we call it R Core Bor. And it's basically in the constellation Corona Borealis, which is called the Northern Crown, and it's between the constellation of Hercules and Boötes. It's right now in the eastern sky at this time, so it's really easy to see now. But this star is also a prototype for the class of variable stars called R Core Bor stars. And it has an irregular period also. And it's called an upside down nova or reverse nova, because most novas are very dim and all of a sudden they become very bright. They may not have been visible to the naked eye before. And this is called a reverse nova because it's actually a relatively bright star at magnitude 6. And it stays around magnitude 6, but then all of a sudden it becomes dim where it drops about 8 magnitudes. So this is one of my favorite stars and one of my favorite type of variable stars. And these stars are usually older stars. They're hydrogen poor. As you know, most stars shine by burning hydrogen, converting hydrogen to helium. But this is an older star where it's used up most of its hydrogen, and it starts to form elements that are heavier than hydrogen. So this is a very carbon-rich star. There's a lot of carbon in it because it's depleted its hydrogen and it's starting to make carbon. So right now this star is up and is in the eastern sky, just west of Hercules.
Yeah, we have a live view of it right now, actually, if you want to take a look.
Sure.
Derek, I don't know if you can spotlight my screen here while we're doing a screen share.
Barbara, if you just go ahead and hit the end share up at the very top, you'll see a big kind of highlighted in red. There you go. Okay. Perfect.
Cool. Yeah, so this is a live view of our Corona Borealis. Let me see if I can make that front and center here. There we go. And we have our telescope out in the driveway right now staring at it as we speak. It's pretty low in the sky right now, but we're still getting a good view of it. And there it is. And it looks to me like there's like sort of a little bulge on that. Do you see that? I'm not sure if that's real or if it's a tracking error, but it does seem like there's sort of something,
Yeah, I do
some
see
irregular
that.
shape going on
It
there.
almost does look
Mhm.
like a guiding. Are you not guiding? Are you, Frank?
No, no, I'm not.
No, you're just checking. Yeah. Is there anything irregular about this, Barbara?
No, one thing it might be is it might be saturated for
Mhm.
your, camera. So,
Yeah, definitely. I was
it,
just
it,
curious if it
it
was
might be because of that. But yeah, it really doesn't have any regular shape to it. And we can go to the AAVSO website and see what it's measuring now, because usually this is a pretty popular star, and usually we have several observations of it every night. So I'm going to look on the AAVSO website and see what the last measured magnitude is for the star.
It's probably worth,
Okay.
saying for our viewers that magnitude works kind of backwards from how you might think, right? Where, higher numbers actually means it's more dim, right?
Right. Yeah. So a magnitude 2 star compared to a magnitude 10 star. A magnitude 10 star is going to be the dimmer star. Uh, and usually if you're away from city lights at a really dark location, you could probably see up to magnitude 6. Uh, like I live out in the country in a rural area, and I usually can see magnitude 5 up to magnitude 5. Um, but the last, there were there were 3 observations on the morning of the 8th of Arcorbor, and they were about 6.3 to 6.4 magnitude were the estimates for that. Um, it's been a few weeks since I observed it, but it stays around 6, 6.5, 6.8. So I usually observe this with a DSLR camera, usually a 20 or 30-second exposure is what I do to measure it.
Great.
And with it, I'm trying to remember when it last jumped to down to magnitude 14. And when it gets that faint, I usually use my large telescope and a CCD camera to measure it. So I've measured it at all of its stages from the regular 6th magnitude, which it stays at most of the time, to when it drops down to 14th magnitude.
So
And magnitude,
in the
go ahead.
period for this variable star is how long? Because maybe we can look at this again in another episode and compare it.
Yeah, it's a very irregular period because I can't remember it. I'm sure it's been over a year that it's been 14th magnitude. Um, let me look.
And while you're
Yeah,
looking
the
at that,
period is very irregular.
I'm going to quickly share our stellarium here for those that are
Mhm.
interested. We're going to zoom in here. There we go. Of course, here, this is the constellation Corona Borealis here. I'm going to go ahead and bring up our labels. So Corona Borealis, as Barbara mentioned, is the northern crown. It's over in the eastern sky right now. The way to find it is basically you want to look over towards the north, and you're going to find the most famous asterism or object in the sky, the Big Dipper. Here we have the bowl of the Big Dipper, and here we have the 3 stars of the handle. And what we're going to do is we're going to take these 3 stars of the handle, and we're going to basically arc over to this bright reddish star called Arcturus. And as Barbara mentioned, this is Boötes. This is the herdsman Boötes. And essentially, just below Boötes, you can see Boötes kind of makes the shape of a kite. Kind of like, look at that, you got a kind of a diamond frame here. And the 2 stars here in the kite shape, if we go just below that, we eventually arrive to almost looks like a little, almost looks like a necklace. I see it more like a necklace with the bright
Mhm.
star called Alphecca or Gemma that goes by 2 different names. But this star right here, this star, let me zoom in a little bit more. So you got the really bright star right there, kind of in between these two stars in the middle of the crown. Just over to the left of it, you'll see the star right here, and that is our this is our variable
Arcor
star.
Boar.
Arcor Boar, yeah. So that's what you can see. If you wanted to take a look at this with your own telescope at home, and you wanted to take some studies with it, this is kind of where you want to look in the sky.
And also, this is a star also that you could take a pair of binoculars and look at it with binoculars and estimate the magnitude of it. This is a good visual variable star that can be monitored visually. And also something else I want to point out, like suppose you do want to follow Arcor Boar with binoculars, and you go out and you look and you try to estimate the magnitude, and all of a sudden it becomes dim and you can't see it at all in binoculars. There are something called fainter than magnitudes that are just as important as estimating the magnitude. So you can still report that estimate to AAVSO. Like very near Arcor Boar is a 7.4 magnitude star. So suppose you go out in your yard and you take a look with binoculars, and you look at Arcor Boar and it's not visible, but you can still make out that 7.4 magnitude star in binoculars. You can still report that observation to AAVSO as a fainter than magnitude. So you can say, okay, on this date at this time, I observed Arcor Boar. I couldn't see it, but it was fainter than magnitude 7.4. So fainter than magnitudes also are just as important as the actual magnitude of a star. Like one of the things that I do with AAVSO, besides my favorite stars that I follow on a regular basis, I look at what are called alert notices. And alert notices are requests from professional astronomers where they'll say, well, I'm going to be observing this particular star with the Hubble telescope. I need to monitor it before my time on the Hubble to see what's happening with the star. Because if it's a star that's normally 15th or 16th magnitude, but it can become as bright as 8th magnitude, that might be too bright for the Hubble and can injure its equipment. So before their planned time on the Hubble, they may send out an alert notice to AAVSO observers and say, I need to know what's going on with this star before this date that I'm going to be observing it with the Hubble. And that an instance like that also is a good time to report a fainter than observation. Like if you go and you look at where the star is supposed to be and you don't see it at all, you know that it's fainter than a certain magnitude, and that is valuable information to someone who's ready to observe that star on the Hubble. So fainter than observations are as important as the actual magnitude that you're estimating.
Excellent. That's awesome. Do we have any other, Frank, do we have any other variable stars that we can look at in the sky right now?
Yeah, right now I'm pointing at Y Canis Venatici, and I don't know if you have a slide on that, Barbara.
Yeah, let's go back to that.
Yeah, if you want to share your screen again, we can head back to your slide deck.
Okay. This is my image, a DSLR image of Arcor Boar. Here's the necklace that Derek was pointing out. And there it is right there. And I don't know if you could make out that little star, but that's the 7.4 magnitude star that I mentioned earlier. And what star did you?
Right now we're looking at Y Canis Venatici. I'm not sure how to
Okay.
pronounce that, but I think that's close.
Yeah, it's Y Canis Venatici, and
Venatici,
it's
yes.
It's also called La Superba, and it's one of my favorite stars because it's a bright red star. It's not real obvious in my photograph here, but it's actually right here. Um, let's go back.
Ooh.
It's kind of easy to find. Here's the bowl of the Big Dipper. And here's the constellation Canis Venatici, basically the two brightest stars, Alpha, which is Cor Caroli, a double star, and then this is Beta, the Beta star in that constellation. And here's why Canis Venatici. It's called La Superba, and it's also an irregular variable, but it's I like doing this either with binoculars or a DSLR because I like to see the red color of it. Like I said, in my image here, it's not very prominent because I'm not really zoomed in, but it's a nice red star that I like to observe. Like I said, it has an irregular period. It's not as predictable, but it varies between 4.8 and 5.8 magnitude. And it varies over a period of approximately 267 days, but it could vary. And that's one reason why we observe variable stars regularly, is that sometimes we may have a period of a variable star that's known to like a thousandth of a hour, and but we still observe it on a regular basis, even though we know that it's going to change its brightness over that period of time. Sometimes they surprise us, where it's a period of 5 days, but instead of 5 days, all of a sudden in 2 days it becomes brighter and it does something strange. So that's why we observe them regularly, looking for unusual activity. Um, so even though variable stars are variable, many of them are predictable, but that predictability can change depending on what's going on with the star, and that's why we observe them constantly.
Mhm. And we've got a good live view of this one right now, and if we can cut to my
Let me
screen
stop
here.
my screen.
There we go. And let me see if I can make mine. There we go. So yeah, you can see it's a lot brighter than our corona borealis. You know, it's just saturating a lot more of the pixels on my sensor there. And I kind of wish I had a color camera right now to get that rich red color you were
Yeah,
talking about.
this is a fun star to go out and look at with binoculars. And let me look up and see what the last estimate
And
of it.
while Barbara's doing it, I can go ahead and share our location in Stellarium. So right now, this object is just above, so we're looking pretty much due north. We have the famous star right here, Polaris, our North Star, with Ursa Major. And basically, we take the two stars and the top bowl of the Little Dipper, and we go up back towards the Big Dipper. What we want to do is, instead of arcing over to Arcturus this time, instead of doing this, heading down to Corona Borealis, what we want to do is we want to look for this star right here in our in the three stars of the handle of the Dipper, and we're going to go just above that, and we'll see Canis Venatici right here. These are the hunting dogs, and if we go ahead and move up here, we can see we have Alioth, and this is Mizar. We have Alcade here. And if we go just above that, kind of in between Canis Venatici and the handle of the Dipper, or the tail of the bear, Ursa Major, we'll see right there is that nice kind of reddish star. And we'll go ahead and zoom in even more, and we can get that really nice La Superba red star there. Look at that. So we can see. So this would be a really nice target in a telescope to see that beautiful.
So in a pair of binoculars also.
In a
like
pair of binoculars, yeah.
Yeah,
So,
when I'm out back walking the dog, I'll take a pair of binoculars, and it's a nice binocular target. And right now, it was measured, the last measurement was on May 5th, and it was measured at 5.5. So that's a magnitude brighter than Arcor-Bohr. So, and it can become as bright as about 4.5.
Oh, wow.
Yeah, definitely brighter. It's plain as day here.
Yeah, so
Great.
that's one of my favorite binocular targets, where several of my measurements aren't using a camera. I just go out with a pair of binoculars and look at it.
Mhm.
And also, I'll, one of the benefits of the AAVSO, like I said, the way you estimate the magnitude of these stars is that you compare it to other stars around it, but you have to know what the magnitude of those other stars are. And you can go to a planetarium program and click on a star nearby and see what the magnitude is. But the AAVSO has prepared um, charts for different variable stars, and it lets you know which stars around your target variable star to use for comparison stars, because some stars around your variable may also be variable, so you don't want to use that to estimate your brightness of your variable. So they determine which stars are stable enough, and they have done photometry on them to know the exact magnitude of them. Because sometimes, like if you look at point to a star in a planetarium program, one program may have it as 5.4 magnitude, one may have it as 5.2 magnitude. So it's not reliable using a planetarium program to find the exact magnitude of stars you want to use for comparison. You can go to the AAVSO website and you plug in. I'll go to the website later and show you how to do this. But basically, put in the name of the star that you want, and then you could also tell what field of view. Like if you're, for my binoculars, it's a 7.5 degree field of view. So I'll say, show me stars in a 7.5 field of view around this particular star. And you don't want stars down to 14th magnitude for a binocular view, because you're not going to see that. So I'll say, show me to 8th magnitude all the stars in this particular field of view around this particular variable star.
Yeah, actually, Barbara, you brought up an interesting point. Is there a way that you could share the AAVSO website? Basically, all you'd have to do is just.
Yeah, I was going to do that in a
Great.
little bit.
Okay, so Justin, do we have anybody in the audience that's watching have any questions so far? Anything that's mentioned here? A variable star.
Yeah, definitely. We actually, you guys answered a couple of them. One of them was the magnitude numbering system. That was a question that came up, but you guys covered that, so that was excellent. Barbara, earlier on you mentioned parsec, and we had a question about parsec distance related to light years.
Yeah, there are 3.26 light years in a parsec. And so you'll hear parsec mentioned instead of light years sometimes, because the universe is so vast that light years becomes the big cumbersome numbers. So sometimes you'll see parsecs mentioned as far as distance. And the way to equate it is that one parsec, one parsec is equal to 3.26 light years. And in a lot of journals, you might even see kiloparsecs or megaparsecs, meaning 1,000 parsecs or 1 million parsecs, because the distances are so vast. So for close objects, for close stars in our solar system, usually we use light years or parsecs. But when you start to see mentions of galaxies and quasars, which are very, very far objects, their distances are usually given in kiloparsecs or even megaparsecs.
So what you're saying, is that Han Solo did the Kessel Run in 36 light years, right? Is that
3.26 light years?
I knew you were going to go there.
Yeah, you had to.
I couldn't resist.
Well, you piqued everyone's interest when you were talking about Betelgeuse going supernova. Can you talk a little bit about how often we see supernovas and when we might see another one besides Betelgeuse?
Well, I'm trying to figure out how many we see in a year. Probably 20, 30 in a year, but they're usually in other galaxies. The majority of the supernova are in other galaxies. It was 1987 was the last time we saw a supernova that was close to us, that was really bright, and that was supernova 1987A. One of the things that is important with supernova is that there are two types of supernova, type 1 and type 2. And then even the type 1 are divided into type 1A, type 1B, and type 1C. If they find that a supernova is a type 1A, they can use it to estimate the distance to the galaxy that it exploded in. So those are similar to delta Cepheus stars in that they can be what are called standard candles and used to measure the distance to the galaxy that they're exploded in. Another one of the things also about the study of variable stars is that we only know supernova once they explode. What we would like to see is a star that we monitor on a regular basis, and then all of a sudden it becomes a supernova. So we're looking for progenitors of supernova. And one of these progenitors are type of intrinsic variable stars called cataclysmic variables. And one of my favorite ones, and I don't have a slide on it, and it's not up at this time yet anyway, it's called SS Cygni. And it's a cataclysmic variable, meaning that when you look at it, even a long exposure, it looks like one star. But it's actually a binary star system consisting of a white dwarf and either a main sequence star or a red giant star. And usually these stars are close enough that the white dwarf will accrete or take gas from the larger star, and something called an accretion disk will form around that white dwarf. And all of us, every now and then, and for SS Cygni, I think it's about every 60 days, enough mass will accrete that a little thermonuclear explosion will happen. So it'll go from 12th magnitude to about 8th magnitude every 60 days. And so these stars are called a type of cataclysmic variable stars. And they think that a type of star like that may be a progenitor to a type 1A supernova. And so that's another class of stars that I like to follow, these cataclysmic variables called, and in fact, the SS Cygni is a prototype of that particular type of variable.
Well, maybe,
and what I mean by prototype is that sometimes the first star discovered that's a particular type of variable star, it's the prototype of that star. So they'll find other stars like it, and you'll hear sometimes that it's an R-core board type star, or it's a Myra is the first variable star that was observed. It's in the constellation Cetus. So you'll hear stars that people will say, oh, it's a Myra type star. So there are prototype stars for each category of variable star. And SS Cygni is a prototype of the type of variable star that has a white dwarf and a main sequence type of companion to it.
Well,
Excellent.
hopefully in the summer, especially later in the summer when Cygnus will be up in the sky, we'll be able to take a look at that interesting.
Yeah, and it's perfect for me because normally I go to sleep and I wake up and I start at about midnight until dawn. So most of my observing and it's, you know, usually by 2 or 3 o'clock is high enough that I'm doing the stars in Cygnus. So for me it's fine, but for most people who don't stay up that late, um, you'd have to wait until summer.
So I believe Frank has another variable star to look at. What do you have, Frank?
Yeah, we're pointing at W Ursa Majoris right now, and it's a pretty good view. So if you want to get to that one, we can talk about that too.
There it is.
There it is.
Now, what's interesting about that star? Let me go back to my lecture. One of my other favorite class of stars are called eclipsing binary stars. And like I said, eclipsing binary is a 2-star system. Sometimes you can actually see them as 2 different stars. But sometimes you take an image and like W Ursa Majoris it looks like 1 star. And actually, I wish I had included an image in my star. With my CCD camera, it looks elongated. And it's because depending on where they are in their orbit, if they're next to each other, it looks like a little peanut. So it's a binary star system where 1 star is orbiting the other, and they undergo mutual eclipses where and sometimes, most of the time, 1 star is bigger than the other. So if the big star is eclipsing the smaller star, the light will drop, but a little bit less than if the small star is eclipsing the larger star. But W Ursa Majora is one of mine, and actually. It's actually a relatively bright star. Its baseline is about 7.8 or so. And it drops to about 8.4 magnitude when it's in eclipse. And this one I did recently with the DSLR. This was March 29th, actually. So this is my comparison star. Like usually we use at least two comparison stars. One to determine if our comparison star is not variable, because all of a sudden, I mean, new variables are discovered all the time. And a lot of times they're discovered because we're using a comparison star, and all of a sudden we're getting some dimming of that comparison star. But this is a light curve. A light curve is like I said, you plot the time on the x-axis, and you plot the magnitude on the y-axis. And this was with the DSLR camera. It took an image basically every 15 seconds for, it looks like about 3.5 hours, a little over 3.5 hours. And so basically I took all of those images of an image every 15 seconds, and I measured the brightness of the object. And then, and the software does this. So I basically take one image, like this is my image, and I tell the software, okay, this is W Ursa Majora that I'm interested in. So I'm going to measure the brightness of this, and I want to use this star and this star as my comparison stars. And I basically tell the software what these magnitudes are, and it would go through every image and then calculate what the magnitude of this star is. And then it would plot a graph for me and show me a light curve. And so this star, this is the middle of the eclipse around right here. And also there are programs called an ephemeris, and it tells you when to expect the eclipse. So like this eclipse occurs, what's the period of this star? I don't remember, and I don't have it with me, but it basically says, okay, on this date at this time is going to be around the middle of the eclipse. And so we'll start observing it at that time. And sometimes we'll observe it at other times also in case something else is happening, because sometimes we've discovered a three-star system, binary system that are eclipsing each other by finding that there's a drop in the magnitude at a time that we're not expecting it. And we've also found extrasolar planets around binary star systems by finding unusual drops in magnitudes when we weren't expecting it in a eclipsing binary system. So this is another one of my favorite class of stars is eclipsing binaries. I love doing light curves for those. And there was another one. This one is called ZZ Sig, and it's another one of my favorite eclipsing binaries. And this one is done with the CCD camera. It goes from about 10.7 magnitude, and it drops down to about 11.7 magnitude when it's an eclipse. So this is another one of my eclipsing binaries. So this is one of my favorite, and this one, you basically, like this takes several hours of observing, so it's kind of on autopilot. So usually, like with the big telescope taking images of this particular star, I may be out with my DSLR and my tracking mount doing other variable stars, while this one's on autopilot collecting data for this eclipsing binary for 4 or 5 hours. Now, I think it's visible, Barnard star, which I just passed. Let's go back to that. Barnard star is a famous star, and it's usually most famous for being the fastest moving star in our solar system. It has a very large proper motion, and proper motion means that the star, like every star has a proper motion. Every star moves in relation to other stars around it, and most of the time it can take thousands and even millions of years to see a change. Like 500 million years from now, if you were on Earth and looking at the Big Dipper is not going to look like the Big Dipper, because those stars are gonna change. There's proper movement, but usually it's not that significant that you can see it in your lifetime. But Barnard star is known as the fastest moving star in our galaxy, and it moves about 10.3 arc seconds a year, and it can easily be noticeable. And this is a project that I started back in 2004, where I actually take an image of Barnard star. I usually do it around the first week in June, and then every year at the same time, I take an image of it. And this is a composite image of pictures of Barnard's star between 2014 and 2019. And it basically shows you how the star is moving in relation to the other stars around it. So it's a real neat little experiment that that I do every year. So it's almost coming up time for me to do my 2020 image of Barnard's star. But besides being a very fast-moving star, it actually is a variable star too, where it actually changes its brightness. It's called V2500 Ophiuchus, and it's an irregular type of variable star, and they actually don't really understand the variability of Barnard's star. It's also a very close star. It's about 6 light years away. So it's one of the closest stars to us. But what's interesting about this star is that they have discovered that it's variable. They've known that it's variable for a long time. And it doesn't change a whole lot, like probably a tenth or half a magnitude at the most. But what's interesting recently about this star is that in 2018, they've discovered that it has a planet orbiting it. It's called a super Earth. It's about 0.4 astronomical units away from the star, and unfortunately, it's not in the habitable zone of the star. And the habitable zone is defined as, if you look at a particular star, there's a zone around that star where if you find a planet, that planet has the potential in that position to have life. That it's called the Goldilocks zone, where the star isn't too close to the star and becoming too hot, or it's not too far away from the star and making it too cold. But it's in what's called the Goldilocks zone, where it's in a region in orbiting the star that life can potentially develop on that particular planet. So the star, the planet that was found orbiting Barnard's star isn't in its habitable zone, but it was interesting that they found a star, a planet around this star, which is one of the closest, it's not the closest star to us, but it's actually, I think, number 4 if you count the 3 Alpha Centauri stars. Then this star would be the 4th closest star to us. So is it visible, Frank?
No, I checked. It's only like 5 degrees above the horizon right now, so definitely
okay.
behind the trees for me.
Oh, okay.
Well, we could definitely take a look at this another time, on another date. So we'll definitely archive this for our viewers to take a look. But we do have, let's go back to W Ursa Majoris. Let's take a look more at that one. Because Barbara, you mentioned that there might be a particular shape to it because of it being a eclipsing binary.
Yeah, let me see. Yeah, let me see if I can find my CCD image of it. It doesn't show up on my when I said that I just did this recently, it was with the DSLR camera. But if I look with the CCD camera, which has a pixel scale where it's easier to separate the stars, it does, you can see the shape of it. Let me see if I can pull up the
so
image.
while you're looking for that, Barbara, if you don't, let's go ahead and take a look at the star that Frank has on his telescope, if you don't mind, so we can give our viewers a chance to see this in real time. So Frank, what do we got?
Yeah, this is it. W Ursa Majoris. Let me take the spotlight here. And I've got my camera in a mode here where I'm sort of sacrificing resolution for sensitivity. So it's kind of tough to split binaries when it's in this mode, but we might
Right.
see like a bit of a bulge to it maybe. Let's see. I'll zoom in as much as I can. Yeah, so I've looked at this a couple of times from a couple different exposures, and I think I see the hint of something up in this region of the star. It's kind of hard to say, but when I look at the other stars, they seem to be streaming in this other direction.
Right.
Tracking
Yeah, I can see
issues,
that.
whereas
Yeah,
this one is more in that direction. So I
that
think
that
there
might
might be a
be.
companion around there.
I meant to do this earlier to bring up that image where, because when I first did this star, I was wondering what was wrong with it, because normally binary stars, we know they're binary, but we see them as one star usually. It's rare that these types of binary stars, you could actually see them as two different stars.
Right.
Uh,
Exactly. Yeah.
okay, let's
And
see.
while doing that, I can show everybody where the star is in the sky.
Yeah,
So here we have Ursa Major again. Of course, we can see Merak and Doobie. These are the two pointer stars that head down to Polaris here. And we're going to kind of head over to kind of the neck region of the bear. So this is the bear's nose. It actually has a funny name, Musca. Think of I think of the mucus of in the nose, but kind of heading down towards where you would see his front leg here. We have that star right here, and that is W Ursa Majoris right here. So again, kind of in this region of the sky where we have our kind of lower, like where his legs would meet, where his kind of shoulders, if you will, of the bear. We can find this star.
Cool.
So, Justin, any questions from the comment section?
Sure, yeah, we've got a couple more. We had a question, Barbara, about when you were using the filters for observing the variables. Why would you want to use different filters while you're studying these
okay.
variables?
Yeah, for almost all the variables, if you're doing digital imaging, either with a CCD camera or even a DSLR, like when I'm doing DSLR photometry, for those of you who know about DSLR cameras, the way they get the color is that there's what's called a Bayer layer over the CCD chip, where it's basically red, green, and blue filters over the chip. And what we do in CCD photometry is we're taking the color, we're separating those colors out and using them as a filter. Like the majority of images in the AAVSO database are green filter, or they actually call it photometric green. And it's similar to, it has a peak wavelength that's similar to what our eye sees as far as the peak color. So when you're observing variable stars, you usually are doing it through different filters. And the most common is the green, or what's called the V filter for photometry. And if you're doing DSLR, when you take your image, like in some of my DSLR images, I've shown the color image because I like to see the pretty colors of the stars. But actually, when you're measuring the magnitude, you're actually taking software and you're separating your DSLR image into the red, green, and blue filters. And I usually will submit just the green data, but sometimes it's important to see what the star is doing through all different colors. So sometimes I'll submit what the magnitude is in the green, the red, and the blue. Uh, and for my CCD camera, I have red, green, blue, and infrared. Some people do ultraviolet, have an ultraviolet filter also. And so they'll measure the star through all those different filters. Um, so for most variable stars, it's important to when you submit your measurement, you have to specify your filter. And it's most of what they want are filtered observations, either green or blue, or red or infrared, whatever. But one group of stars that it may not be as important to have color information is eclipsing binaries. Because eclipsing binaries, you're not as concerned as what the exact magnitude is. You're more concerned with what time something is happening, like what time the eclipse is happening. And so it really doesn't matter whether there's a filter used. So in those instances, if you don't have a photometric filter, or um, you basically can just use a clear filter or no filter at all and measure the magnitude, because the timing is what's more important in that case. Uh, so it's important, if you get really serious, and especially with a CCD camera, you do need to have photometric filters. And I have a set of 4, red, green, blue, and infrared. But probably 90% of CCD um, photometry people only use the green filter. So at a minimum, you do need a green filter if you're going to do CCD photometry. But if your
Nice.
goal is to do, like I love doing eclipsing binaries, and I do use filters for those also because I have them. But it's not as important to use filters in that case, because we're mainly interested in the timing and not necessarily the absolute magnitude that we're going to get from that star.
Great.
Well, we might need to do an entire show on supernovas, because people are just loving this idea. We talked about telescopes viewing supernovas throughout other galaxies, but what do we have in the historical records of human civilization where supernovas have been recorded by different civilizations?
Yeah, as probably as early as I think 1054, the Chinese have observed bright stars that have appeared, and nova itself basically is Latin for new star, and so it goes back a while where different cultures have observed new stars in the sky that have disappeared after a few months, and these were supernova. Um, like one famous supernova remnant is the Crab Nebula, and unfortunately it's set already, but it's in the constellation Taurus, and it's basically a supernova remnant. It was a supernova that happened. I think this was in a 1054 supernova, and once the light from the supernova dies down, and the star basically disintegrates, there's a remnant that's left over from that exploding star, and these are called supernova remnants. And M1, the Crab Nebula, is probably the most famous supernova remnant.
Yeah, so interestingly, there is an object in the sky right now, Barbara, M100, and I think right now there is a supernova going off in it at the moment. And Frank, I think you have that in your telescope at the moment, right?
I do. I read your mind, and I remember taking a picture of this last year when that supernova was definitely visible in it. I'm not sure if it's
Let's see if
still
we can
there.
let's see if we can
yeah.
reference that picture.
In fact,
Yeah.
while you're doing that, let me, not only do I do photometry of regular stars, but when there's a supernova out there, I also do photometry and measure the brightness of those. So I'll bring up images of some supernova that I've measured the brightness of.
Fantastic.
But yeah, here's M100 live and a bunch of companion galaxies too. It's like a whole cluster of them here, which is cool in and of
Nice.
itself.
Mm-hmm.
But yeah, I don't quite remember where that supernova was in the galaxy. I want to say it might have been that one right there. I'd have to look it up to be sure, but
Yeah, let me check it out, Frank, because I think you sent a picture, didn't you?
Yeah, I did have an annotated picture of that at one point. I could pull that up myself, actually. Let's see.
Yeah, let's take a look.
Yeah, let me see if I can dig that up real quick. M100. Meanwhile, bask in the glory.
Yes, beautiful, beautiful galaxy here, and nice spiral galaxy. It's actually located in kind of Cobra Berenices in that area. It's actually part of that super cluster of galaxies that's found here, along with M98, M99, and M100, of course, being this one here. Right now, it looks like here the distance of this galaxy, trying to get that information right now. Well, I know the size of it is roughly about 130,000 light years across, so quite a large galaxy. It's about 14 megaparsecs. So for those that were listening to Barbara earlier, you could figure out what the light years of that is. So 14 megaparsecs. But if you didn't want to do the math, it's about 47 million light years away. So quite a far object.
Yeah, and I'm not seeing the supernova in this image. I think it should be like right around here, so it might have fizzled out already. I can share the image from last year here.
Yeah, go
share
for it, because I think it's really neat to show that these things happen.
Yeah.
Change and the light from these objects change, and there's delay and all this good stuff.
Yeah. So are you seeing that? This is should be a
Yes.
browser image. Yeah. So that's the same Galaxy M100 that we were just looking at and blown up. And you can see this annotation here. We had supernova 2019 EHK that was showed up right near the core there. So yeah, that was something that I could see from my driveway in a pretty modest telescope, which is pretty cool. It's supernova in another galaxy.
Well, I can show. I have a slide of some two galaxies that I measured the.
Yeah, I've relinquished the screen to you.
Okay, let's see. This one. Okay, this is two supernova that I measured. The one on the left here, this was what year was it? 2014 was the supernova in M82. So this was a pretty bright supernova in the galaxy M82. So this was April 23rd, and I measured it at 11.7 magnitude. So not only, so I do photometry on supernova. And this one, you can't see the galaxy that well.
Oops.
And what happened?
Might have accidentally clicked on your mouse to move to the next slide.
Yeah, there you go.
There you go. There it is.
Yeah. Anyway, that's the core of the galaxy. It's not a long exposure, so you can't really see the galaxy arms as much. But this is a 13.028 magnitude supernova. This was in 2017. And I don't remember what galaxy it was. But yeah, that's another thing that when you're doing photometry, it's not just stars. You measure, find out new supernova, and measure the brightness of those.
And of course, looking at supernovas like this, going back to the period luminosity relationship, while discovering these new supernovae, we were able to then calculate not only the distance of these objects, but we're also discovering that these objects are accelerating. They are actually, the universe is expanding. That's what Hubble determined. But later on, when we looked at these new supernovas, and we were able to see this slow change in magnitude variability of these supernovae, we were able to figure out the distance, the changing distance of these objects. And in reality, we found out that these galaxies are actually accelerating, because we know that they are, based on a concept in astrophysics, they are shifting to the red. So they're actually, the wavelengths are expanding, are getting longer as these objects are viewed. So kind of an interesting thing. So variable stars have really opened up not only just the fact that, yeah, galaxies are in other parts of our universe, not just our own Milky Way, but they've also helped us describe the mechanisms of our universe, how they change, how we evolve, things like that. I think these are really incredible. So it looks like at the moment, these are the variable stars that we have predominantly up in the sky. But for those that are watching, when you go outside early in the evening, Barbara was mentioning Betelgeuse. We have Betelgeuse for a very split amount of time. Unfortunately, we're kind of getting away from that season when Orion's visible, but hopefully we'll be able to do some more observations of Betelgeuse when it starts to come back up in the late fall. But Frank, do we have anything else that's really interesting that we can look at?
Oh, there's plenty of stuff we could look at. M100 in its cluster there is just getting better and better with time. I've just been letting that soak, actually. Yeah, let me.
Look at that little galaxy over here on the left of it. We can actually see that there's several other galaxies in that cluster. As I was saying before, this is part of that large Virgo Coma Berenices supercluster there. So again, remember last week we were talking about galaxies. This is a prime time for galaxies observations. So I think it's miraculous. Let's see how many galaxies can we count in this. So we have one, I see 2, 3, 4, 5, 6, 7. There's 8. Any others out there that you see?
And it's only been like 8 minutes on this, and more and more are showing up by the minute.
I know.
There's definitely one right there, right?
Yeah. So there could be at least 9, 10, maybe even more galaxies in this image. And it just goes to show you that each one of those galaxies can contain hundreds of billions of stars and potentially trillions of planets. And that's just one galaxy. And we just see 10 or more galaxies in this image as Frank is exposing more and more. It's just incredible. But through the advancements of variable stars that Barbara mentioned earlier in her presentation, we now know that these galaxies are not part of our own. They are their own galaxies that contain dozens of, there could be somebody right now that's an M100 Barbara doing variable star research in that galaxy. And maybe there could be Jason telling people questions about and then maybe there could be like parallel versions of ourselves, but it's just I think that to me is one of the most exciting things about astronomy is just the unknowns, right? Just the imagination runs wild when you look at these objects and you just imagine yourselves in there. I don't know how you all feel, but I think it's just that's the wow factor of everything. You just feel so just overwhelmed by how much you see.
I know one of my favorite movies is Contact. Yeah. And one of the last lines of the movie is that there basically are so many stars out there. If there isn't life on any of those planets around those stars, then it's an awful waste of space because it's just so vast. And like when you think of one galaxy and how many stars are in that galaxy and then how many planets around those stars, it's just mind-blowing. And like just in this image, looking at how many galaxies there are in just this little field, it just blows the mind.
Yeah, this is less than 1 degree of the sky we're looking at here. And these are just the galaxies that are bright enough for us to pick up. I'm sure there's far more beyond this that we're not even sensing.
think of the Hubble Deep Field.
Mm-hmm.
If people aren't familiar with that, uh, several years ago, they did an experiment with Hubble where they basically just looked at an area of sky that was blank. You couldn't see any stars. It just looked like black space. It just had no stars visible in it. And then they did a very, very long exposure. I don't remember how long. But when they finished, it was just an incredible amount of galaxies in that one field where just on the surface, it looked like it was just blank space, that there were no stars, no galaxy in. But when they did a long exposure, meaning that the galaxies were very, very faint and most likely very, very far away, they showed tons of galaxies. And it if you want to see, just Google Hubble Deep Field, and there's also an ultra deep field, and it's just amazing how many galaxies are in that small amount of space, and how where it looks like it's just empty space, nothing to see here.
And it's
Uh,
about the size of your fist, just to give you
mhm.
an idea of the scale. Frank, is there a way that we can look at the Markarian's chain? We can look at M86, and then we should be able to expose from that. Because we're
Yeah.
talking about galaxy clusters. And I know that we have, we can look up a quick photo of the Hubble Deep Field. I don't know, Justin, can you, while we're doing that, can you bring up a photo of the Hubble Deep Field to show people what Barbara was mentioning? While we get the scopes set up for M86 and the Markarian's chain, which, by the way, is a chain of many, many galaxies found in Virgo. It's a part of that Virgo cluster, and it actually contains many types of galaxies. That's something we didn't really talk about last Star Party episode, is we didn't talk about the types. We talked about some of them, but we didn't talk about all the types of galaxies that we can see. So yeah, look at that.
Wow.
It's just, I mean, blows your mind just how many galaxies are seen in this image. I mean, if you had a magnifying glass, you could just scan this entire image and just, I mean, there's only a few stars in there. You can see that anything that has like a spiky look to it. Justin, I don't know if you can point to that one star. There you go, that one, yeah. Any of those are stars, but everything else is a galaxy. So I think that's just miraculous, just to see how many, and that's just in one tiny little area about the size of your fist in the sky.
I know, and what's incredible is that if you just point to that area of the sky initially, you won't see anything at all. It just looks like black space. But when you expose for longer periods of time, you get all of these galaxies. And
That's,
this is, to me, this is one of the most incredible images from Hubble for me. It's just mind-blowing.
yeah, I remember we
that.
were talking about that during the 30th anniversary of Hubble, and I think was it yours, Justin, that the Hubble Deep Field was your pick for your favorite object?
Yeah, absolutely. That was this one always stood out to me.
And hey, we're talking about the Crab Nebula, and Justin, I see on the background there in your wall, you look like you have the Crab Nebula there. I can see it on your wall there. There it is. So that's that supernova that Barbara was talking about, the Crab Nebula. Is that astronomy calendar that you got? Yeah, there you go.
I should unmute. Yep.
Yeah, so pretty cool. All right, Frank, what do we got? Oh, that's looking good.
We have lots and lots of galaxies, yeah. And I can't fit them all in the frame. Like, this chain of galaxies is just so huge. Like, this is just a portion of this cluster that we're looking at here.
So maybe we can expose some of the other areas. Maybe we can move the telescope on a little bit just to kind of explore some of this area. So the biggest, brightest one in there is M86. That's that big bright one in the center there. That's a large galaxy in Virgo, and this one is about 55 million light years away, or 17 megaparsecs. We're gonna use this parsec thing going on to keep you all fresh on how to use that. But anyways, a couple interesting facts. You know, 300,000 light years across. I mean, it's just incredible. You know, again, all the stuff, and it's actually what I'm reading here is that it's the has one of the highest blue shifts of all the Messier galaxies. So what blue shift means is that it's actually heading towards us, opposed to away from us. And right now the velocity is 280 kilometers a second is the velocity of this galaxy as it's heading towards us. So so that's let me do a little conversion. It's 11 o'clock. I'm tired of, you know, I'm gonna do it the I'm gonna convert it using my conversion here. You know,
Yeah, we're getting loopy.
yeah, well, not loopy, just it's been late. So that's
I'm getting loopy.
173 miles per second. That's the speed of this galaxy as it's heading towards the Milky Way. That's
Wow.
crazy. 173 miles a second. A second. So pretty wild.
Yeah, and as we get more and more time on this exposure, we're getting more and more details on these galaxies surrounding it too, which is really cool. Some of those dust lanes are coming out on these two galaxies here. They must be edge-on spirals, I guess, right? Yeah,
that's right. Yeah, that's right.
And up here, we have some like some hints of wispiness coming off of those two up here as well.
I see that.
Are those the eyes, or am I in the wrong part of the sky?
I'm not sure actually.
Yeah,
take a look.
need a little bit more context.
Yeah, need a little more context on that. Yeah, but let me take a look here. So, and by the way, that one is actually M84 that we were looking at, not M86. So again, 11 o'clock at night for us here. That was M84. M86 is next to it, which is just off to the just below it there. That brighter one here just below M84. So that's M84. It's a lenticular galaxy. And a lenticular galaxy is kind of a football shape, very similar to an elliptical galaxy. Elliptical galaxy is basically a spherical stars, a galaxy of stars, unlike a spiral galaxy, which is kind of a spiral shape, a very flat. Elliptical galaxy is very, very dispersed, very much more of a rounder shape. But a lenticular galaxy is kind of more of an oval shape of an elliptical, a little bit more like a football. So we have lenticulars, we have ellipticals, we have spirals, we have edge-on spirals. You know, again, as you can see here, we have lots of different varieties of galaxies that we see in just this image alone, which is pretty crazy.
Yeah, there's more popping out.
And speaking of different types of galaxies, if people are interested in a little project, there's something it's called Zooverse, I believe.
Zooniverse, yeah.
Zooniverse, and they have a project where they send you images of galaxies, and you try to classify what type of galaxy it is, whether it's an elliptical galaxy, a spiral, or irregular. And they need people to classify these galaxies. So I think that is still going on. If someone is interested in working on a project in front of their computer, is classifying these galaxies.
Yep, more citizen science.
Yep.
Cool.
So, Barbara, you mentioned earlier that you were going to show us a little bit about how we could use the AAVSO to look at the magnitudes of stars. Is that something that you can show?
Okay. Let's go back, and I'll bring up the AAVSO website and show what's available there. Okay, so this is the main page of the AAVSO website. You can learn about the organization. They have forums also where you can discuss different topics. You want to talk about a particular star, you want to talk about a method of observing, and so there are all types of different categories in the forums. This it tells you about variable stars, and then the observing tabs. Like there's an observing section that shows um, where you could go into different observing sections that talk about particular stars. Like I hang out at the eclipsing variable star section a lot. And let's see, another one. This one, I love the short period pulsating variables. They're kind of like eclipsing binaries, but they have very, very short periods of like an hour or two. So I like those a lot. But they also have observing manuals. And you don't, for what I'm showing you now, you don't have to be a member. And it's a good idea to join that. It's not very expensive. But like if you want to download a PDF copy of the visual observing manual, and it instructs you how to observe visually variable stars. DSLR observing manual. So these are all the observing manuals that you can download as a PDF file. Data. This is where, like if a particular professional astronomer is interested in all the data on a particular star, and they can go back, the AAVSO started in 1911. They could say, give me the last 100 years of data in your system on SS Cygni. And so they can go and download and examine that data. And it's not just limited to professional astronomers. If you just want to look at the history of a particular star, you can say, show me data for the last 50 years on this particular star. But the main section, like if I'm interested in SS Cygni, I would go here where it says pick a star and type in SS Cygni. And you have to know the nomenclature of variable stars also. So if I want to look at the most recent observation of it, I click on recent observation. And eventually it'll come up. And this is a popular star, so it usually has several observations. So the last observation was May 8th, and it was at 10.9 magnitude. It was observed visually. So either someone probably with their telescope, just looking through the eyepiece and making an estimate. And this is a star that every 60 seconds it goes from about 12th magnitude to about 8th magnitude. So you can see what it's been doing lately. Also, if you want to create a chart for this particular star, you just click on plot a chart, and this is where you put in information. So like if I want a chart on SS Cygni, and you can be pretty specific. Like for my CCD camera, it has a field of view of 26 arc seconds. So I want to put in that field of view. And I usually put in a limiting magnitude of about 2 magnitudes fainter than how faint that star gets. So it usually gets to about 12th magnitude. So I'll put in a limiting magnitude of 14. And I can give it the orientation that I want. Like if it's in the east part of the sky, then for my camera, it's north down and east to the left. And it's going to tell me the comparison star magnitudes. I want it in blue and red filter also, because normally those are the filters that I observe it in. And then I hit plot a chart. Oops, what happened? Oh, I put, let's delete. sometimes if you don't want to put a particular star in, you can just put coordinates in and say, show me all the variable stars around these coordinates. So that's what happened. But you can't do both. You either put a star in or the coordinates. Okay, let's. What happened? Okay, okay, let's take these out. And take that out and then plot. Okay, so this is my chart of SS Cygni. And so I'm not sure why it's not labeling. Oh, I know what I did. Okay, let's try it again. Okay. Okay, so it gives me a chart. The chart's title is SS Sig for SS Cygni, and it shows you a cross in the middle. That's where the your star is. And then it shows stars around SS Cygni and what the magnitudes are. So I could pick either one of these stars to use as a comparison star. And usually you want to use a comparison star that is about within 2 magnitudes of your star that you're measuring. And that's why it shows different magnitudes. So like if it's on the brighter end, you want to use this comparison star. If it's on the fainter end, you want to use this one. But it basically, in my field of view for my CCD camera, these are the available comparison stars that I could use to measure SS Cygni. And so you can get these custom charts for any star that you want to observe. Just go to the website and say, okay, I want to look at Arcor Bohr. The field of view is 7.5 degrees if you're using binoculars. And my limiting magnitude is 8. And it'll basically give you a chart just like this. And you could, just take your phone out with you and look at your comparison stars. Or some people will just print out the chart and take it out to the telescope with them so that they know where and see, it also gives you the pattern of the stars around so you can pick out your variable. So like at 5 o'clock this morning, I measured this one, and I took an image of it. I haven't measured it yet, but I did this one about 5 this morning. And out of every star in the database, I probably have more data on this particular star than any other star. This is one of my favorites. But that's how you get a star chart from the AAVSO. But it's a great website to explore. If you become a member, they have what are called choice courses, meaning that they have, like if you're a beginner, they have a 4-week course on online, and these are online courses on how to observe variable stars. Or they have a course on how to classify variable stars, and they're pretty interesting. But you have to be a member to take these courses. Also, if you're interested in variable star observing, they have what's called a mentor program where you could say, well, I'm kind of overwhelmed, I don't know where to start. And they can assign an AAVSO member as a mentor that they can kind of help you get started. And you have to be a member for that feature also. But I've mentored, I don't do a lot of visual variable star observing, but I've taught the courses on DSLR photometry, and there's 2 CCD courses also that I've taught. One of the courses for that. So someone with a camera and they want to stop, not necessarily stop doing pretty pictures, but expand from pretty pictures to something more scientific. One of these choice courses is a good idea, where it basically assumes that you've had some experience with your CCD camera, and it tells you how to expand and use your camera for variable star photometry.
All right, thank you so
But
much.
I encourage everybody to go to aavso.org and explore the site. There's a lot of information there. And like, even if you want to just read about variable stars, there's a lot of information on the story that variable stars have to tell. Like they do what's called a variable star of the season or the month, and they'll pick a particular star and go very in depth into that star and why it's important. So even if you're not interested in observing variable stars, but getting more information, it's a great website to explore.
Yeah, I spent a lot of time on that website during all the Betelgeuse drama, just keeping tabs on what it was doing. Like, is it gonna blow?
Yeah, the forums were very good at that time to see what the thoughts were on Betelgeuse.
Yeah, and those different filter measurements you were talking about were crucial to really understanding what was really going on with it
Right.
too, right? So, I learned a lot about variable stars just from all that hype around Betelgeuse, and I think a lot of other people did too.
Yeah, and one star that I was going to mention that I didn't, especially when we were talking about eclipsing binaries, one of the more famous eclipsing binaries is Epsilon Auriga. And it's one of the kids in Auriga. And it's an eclipsing binary star, pretty bright, like 3 point something magnitude. And it's one of the longest eclipsing binaries out there that's known, and it eclipses every 27 years. So it takes 27 years for one star to go around in its orbit to eclipse the other. And they had a huge citizen sky campaign. I think it was 2009, which is when the last eclipse was. And they had a lot of people doing just visual variable star because this star was so bright. You didn't need equipment. So there was a big citizen sky campaign that instructed, the average person how to go out and observe Epsilon Auriga and submit observations. And also this is the time when DSLR photometry became prominent, because CCD users, Epsilon Auriga was too bright and would saturate the CCD chip really quickly. But DSL, and that's one of the reasons I got into DSLR photometry, is that there was a bright nova at the time in Sagittarius. And I wanted to monitor it, but it was too bright for my CCD camera. It would saturate the chip. So that's when I got started in DSLR photometry, because you can do longer exposures without saturating your star with DSLR photometry.
Excellent. So we are we probably have enough time for one more object to look at. Frank, do we have anything that you would like to show with the telescope? It looks like you got something going on here.
Yeah, right now we're looking at NGC 4039, and you're gonna have to tell me what this is, Derek. What the heck is this thing?
The
It's
antennae
weird.
galaxy. It's actually 4038, 4039. These are interacting, colliding galaxies.
Okay.
Located in Corvus. I can actually show you all where that is in a little bit. But actually, what's interesting is that this is one of the youngest pair of colliding galaxies that we've discovered. They're about 1.2 billion years old for a galaxy. That's actually pretty young. and they're about 60 million light years away, roughly. But what's interesting is that in about 400 million years, these galaxies will merge into mega galaxy. They'll actually merge together and form a huge super galaxy. And actually, what's really interesting about this is exactly what our Milky Way and the Andromeda galaxy will do in about a couple billion years from now. So this is kind of looking at the future of us. Two spiral galaxies colliding with each other. And one thing that kind of always gets me excited is that when we say colliding galaxies, we don't really mean it. It's like two automobiles hitting each other, right? You know, it actually means that they're interacting. So actually, there are probably hundreds of, billions of stars in these galaxies, and not a single one of these stars will actually collide with each other. They'll interact with each other. They might get close enough where their gravity might be strong enough to pull things away or maybe knock out planets and things like that, but stars won't actually smack into each other and collide with each other. So that's really kind of an interesting thing when we look at these. We don't see these large explosions or bursts from these interacting galaxies. So kind of an interesting thing. We're talking about variable stars. If there were stars that would have collided during this interaction, we would obviously see an increase of brightness in this area of the sky, but we haven't actually seen that yet, which suggests that when these galaxies are interacting, they're not actually undergoing some type of star collision or anything like that. So at least we haven't seen yet. Doesn't mean that it won't happen. It just means that we haven't actually observed that phenomenon yet. So kind of
or also that it's so far away that the light just hasn't reached us yet.
That's right.
Like it happened 1,000 years ago, and
yes,
just
we're
hasn't
time
reached us
travelers.
yet.
We're time travelers in astronomy. We never look at anything, even the moon. Funny, I always tell people, when you look at the moon, you're actually seeing it 3 seconds ago. So even the moon, you're not even seeing in real time. But yeah, so this is the antennae galaxies. This is a really interesting, and as we're starting to expose, you're starting to see, I don't know if you can see it on your screen, Frank, but you can kind of see almost the outer arms of these galaxies kind of almost creating this interesting figuration on the sides there. I don't know if you can see that.
Yeah, it's very faint. We're battling a full moon tonight, so it's kind of tough to pull out that detail right now. But
it's still pretty incredible from a suburban backyard. Let's put it that way.
Totally, yeah. I've always wanted to image this one, and thanks for pointing this one out.
So let me show you all where this is in the sky. So Corvus is, I call it the baseball diamond. It's actually right now in the southwestern sky. And if you look up about 20 degrees above the horizon, you'll see these 4 bright stars here. As I said, I call this the baseball diamond. You got home base, first base, second base, third base, right? And but this is supposed to be Corvus the crow. I can actually bring up the animation here. You can actually, there's our crow there. So, and the antennae galaxy is essentially just you got first and second base here, and go about halfway, and then to the right of that. That's essentially where we're looking at. So if we were to zoom in on this target, we'll be able to see those antennae galaxy there. So there you go. Now, if we expose long enough, Frank, maybe you might be able to see these tendrils,
right?
These arms that have basically been ripped apart as the galaxies are interacting with each other. And again, as I said, these galaxy centers are going to merge together into one major core. But what's interesting is they're going to conserve momentum. They're going to keep going, and they're going to keep ripping themselves apart, and they'll form 2 new galaxies from that as well. So kind of an interesting, again, as I said, kind of a chance for us to see what's going to happen to the Andromeda galaxy and Milky Way by looking at these 2 galaxies here.
Cool.
Very cool. Yeah, I'm seeing some hints of those tendrils there, but a little bit tough to pull that out.
We'll have to take a look when we have no moon out, and so we can get some data on that.
Definitely finding the moon there.
Well, Justin, we have enough time for a few more questions. If anybody has any, we can answer those.
We actually had a telescope question, if you want to hit that. Greg was asking, he just got an 8SE, and he wanted to know best eyepiece that he you guys would recommend to look at some of the Messier objects that we looked at tonight? I know that's probably a deep question, but he's got a 6.3 focal reducer and just wants to kind of know what might be the best eyepiece you guys would recommend to view what we saw tonight.
Well, the focal reducer will help greatly with allowing for a wider field of view. I always enjoy the range of 24 millimeter to about 13 millimeter range of objects with that focal length. I don't know how you all feel about it, but I have a very similar. I have an 8-inch Celestron Edge HD, and I find between 24 millimeter to about 13 millimeter provides a really nice range of views of different galaxies and different sizes. With that longer focal length, you're going to get a little extra resolution power. But how about you all? What do you think? What would you answer with that?
I would say like between 26 and 12 millimeter eyepieces. And that focal reducer helps, especially if you're going to be observing variable stars, because you want to have as many comparison stars in your field of view. Because there are some stars that, that there may be only one star available in your field of view. So the larger the field of view, the better choice of comparison stars. So that 6.3 reducer, focal reducer helps. But you probably don't want to go below 10 millimeter eyepiece, and you could probably go, I think 26 is comfortable, like a 26 millimeter eyepiece.
Nice wide field eyepiece. So
Yeah.
You get a really good view of everything. Yeah. How about you, Frank? What do you think?
Yeah, I mainly agree. I mean, I actually had like one that was about 33 millimeters, if I remember right, that I used to use in the field a lot. And with that particular telescope, it can be tough to point it accurately. So that wider field of view can come in handy for kind of figuring out where you are in the sky and getting some of the larger objects as well. But for Messier objects, like you said, around the 20 to 12 range is probably about right for most of them. I also like to keep like around an 8 millimeter in my arsenal as well for looking at planets, because if you can make Saturn or Jupiter look like huge and beautiful to people, that's always a crowd pleaser. But for Messier objects, yeah, around 20 or so is probably about the right size for that scope.
And that is it for questions.
All right. Well, we're pretty much almost at end time here, and I wanted to really thank Barbara for joining us. I hope you enjoyed our exploration of the cosmos too. You got to see some cool objects through the telescope and sharing your passion about variable stars and sharing. I learned actually quite a lot today too with these variable stars, and I'm actually excited of kind of utilizing my astrophotography gear to do some scientific studies with the variable star research with the AAVSO. So for those that have a telescope or a camera or just a pair of binoculars or just your eyes, there's a lot of science you can do and you can help out contribute to our scientific exploration of the cosmos. And so with that, I want to thank you all.
And actually one other thing, besides what Richard Wright thinks, stars can be very, very interesting.
Oh,
and there are a few books that I'd like to recommend that I found fascinating. This book is called by Sir Patrick Moore. It's called Astronomer Stars, and it's basically just a biography of. He picks basically a star, and basically will just do a biography on that star and why he thinks that star is so interesting. And this is one of my favorite little books. And there's a similar book also that I like. It's called the 100 Greatest Stars. And it's pretty much the same thing, where he would pick a particular star and he would dedicate just a biography about this star and why he finds it interesting. And the book is by James Kaler, and he has a website called Stars, and it's basically any star you could imagine, you just select it, and he has a whole biography on that particular star. And it's one of my favorite websites. Um, and I can't remember the address, but just Google Stars by James Kaler, Kaleer. And it's anything you want to know about stars. And for both of those books, most of the stars are variable stars in here that they talk about.
Excellent. Yeah, well, I can imagine there's so much stuff, and this is a great time to read and to explore. That's the beauty part about astronomy is you can do this in your backyard. You can read, so definitely a lot of opportunities to do some stuff. So get out there. For those that are out there, get out there, do some science, do some exploring. Lots to do, and hopefully we'll have some more clear skies coming up in the future for us to enjoy. So again, I want to thank all of you for joining us tonight for our star party. And next week we're back at it again at 9 p.m. I just want to let you know that once we get into June, we are going to be moving to 10 p.m. because obviously, as we move into closer to the summer, it's going to get darker later. So we're going to start a little later. But we have some really cool. Other interesting things to talk about. So again, Barbara, thank you very much for joining us tonight.
You're welcome.
And of course, Frank, thank you again for sharing us your awesome telescope. And of course, Justin, thank you for just being Justin. Thank you for being our communicator into the Facebook world. And with that, again, thank you all for coming out tonight. And we will see you next week, same 9 p.m. And with that, and for those that are on YouTube, I hope you enjoyed this program, and we'll be uploading more. And of course, be sure to subscribe to us. We upload these usually a day or two after we do our recording on Facebook. But we love to see you and again, please subscribe. And with that, have a great rest of your night, everybody, and we'll see you next time.